Well, thank you for joining me for me to repeat my presentation that I did at Imperial College a couple of weeks ago, Imperial College in London, which is about aging. And there's two things I want to look at. One is the arguments about whether aging is intentional from an evolutionary point of view or an error. And the other one is whether acetylation is perhaps more important as what's called a PTM, uh,
Post translational.
post-translational exactly, post-translational modification. As Walter said, there are lots of different types of PTMs, post-translational modifications, which are changes made to proteins in the cell after they've been created. Acetylation, methylation, phosphorylation. There's lots of ones. A lot of people have studied, particularly the methylation of the DNA, but also the histone, the protein on which the DNA is held, gets methylated as well. But I would argue that acetylation is perhaps more important and methylation follows on from it. Now, it's hard to measure, so it's
Yeah.
difficult. Now, I have a website, citrate.science, on which has a lot of the background papers, and you can see the link down the bottom. But if we go on to the next page, I like to look at creatures, and one particularly interesting type of creature is the bee. And the reason the bee is particularly interesting is that you get queen bees and worker bees. And the queen bee has a lifespan of perhaps 2 to 3 years. And the worker bee, even though they work quite hard, their lifespan is really short. However, their DNA is the same. They're both female and their DNA is the same. And I think most people know the reason why the queen bee is the queen bee is that the queen bee eats royal jelly for her whole life. And the worker bee has it for the first 3 days of their life. And this is an example of exogenous epigenetic control. That is, the epigenome, the way the genes are controlled, is controlled by something external, something in the food. And with ants, for instance, if ants, which have a similar sort of process, if they lose their queen, a worker ant can just change into the queen. Now, I would argue that actually, when you look at how the mitochondria operate, and I'll come to this in more detail later, you need to think in terms of the two linked cycles of citric acid cycles or Krebs cycles, which I would call the citric acid bicycle. And I'll come to that much later. But I always find the bees very interesting. And there was a lot of study done in the 1940s by Thomas Gardner that has been lost because it's not in HTML, so people can't find it. But he did quite a bit of studying about what's in royal jelly. And the question is, what is it that suddenly makes a worker bee able to live such a long period, times longer, maybe 2 or 3 times the length of life? And I would argue it's a histone deacetylase inhibitor, a combination of acetyl-CoA precursor and various AMPK activators as well. But let's not worry about that. The main thing is I think it's always worth thinking about the bees and why is it that the food stuff that the queen bee eats enables the queen to live a very different life. This is a relatively unusual fish. It's called the bigmouth buffalo fish. And it lives for over 100 years. But its eggs are subject to heavy predation and it has negligible senescence. Now, we talk about that with the naked mole rat, and you'll be pleased to know I'm not going to show you any pictures of the naked mole rat, which also has negligible senescence. And interestingly, the naked mole rat is a sort of hive creature, EU social creature, much like the ants and the bees. And the point about the bigmouth buffalo fish is if it wasn't able to live so long, then it wouldn't be able to continue as a species. So the lifespan is set by evolution to cope with a niche where very few young fish survive to adulthood. Here's another one. This is a bat. This is Bechstein's bats. They live in the trees. They don't live in caves. And the lifespan depends on the weather. And a study found that every 10, 15, 20 years, there was a catastrophic weather event which killed a lot of bats off. And so the young are also subject to that. Again, they have negligible senescence. That is, they don't really age in the same way. And what's happened here is that evolution has set the lifespan to cope with an evolutionary niche where a catastrophe every few years kills off a lot of the population. Now, and that's a link to the actual paper there at the bottom. This is an odd creature. It's called the sea walnut, and it can live in reverse. So, in other words, under certain circumstances where it's been starved and then refed, it will regress to an earlier stage in its life. So its health span has a reverse gear. And this is relatively rare. There are very few species that can do this. But I find it particularly interesting because it sort of says, well, there is a program, the program of development that can run in reverse in some species. And if it's conserved, that is, if it's similar in all species, the questions then is, well, what is running that program? What is it that is the system, and how can we, if we wish to influence the program? But the main point about this is that evolution can set a range of lifespan and development styles as well as an average lifespan. So everyone knows about the human lifespan. People are well aware of the fact that worms live a few, mayflies a few days, worms perhaps about 20 to 30 to 40 days sometimes. Mice, rats, I think they aim for 900 in a control for rats. And the various whales last 200 years. But actually, it's more complex than that. It's actually that certain species don't age, but for various reasons, if they didn't have negligible senescence, the species would die off, and that development can run in reverse. Do you want to sort of talk about that at this stage, or should we move?
Yeah. Development can run in reverse. I guess this would also be true for the what do you call it? The worms everybody uses for their tests. The
C. elegans.
Yeah, C. elegans. They also, if you starve them, they go back in time. It seems.
Yeah, well, that's the same. This is the whole question of what is it that causes that. I think it's that when you starve them, you get very serious autophagy, and the autophagy is selective autophagy, which selects for the more efficient mitochondria. So you improve the efficiency of the mitochondria. And I think the biological clock, the fundamental biological clock, is actually the efficiency of the mitochondria. Shall I move on?
Yeah.
Okay. Now, these are pictures of me because I'm a biohacker and I experiment on myself. And as you can see, I've changed quite a bit. Obviously, the difficulty with n=1 experimentation is that anecdote is not, the plural of anecdote is not data. On the other hand, it's a very rapid route to find out if anything has an effect. And it's quite interesting what does. And I think much that I'm not going to go on about my own personal results because I don't think that's a useful thing. One of them is interestingly reversing a cataract. I had preclinical cataracts in one of my eyes, which has reversed. And that's an unusual thing. It's not known to happen in non-diabetics. So I think there are a number of signs of making some progress. To what extent you would see any of this as making progress is a matter of judgment. But I shall move on. My hypothesis for aging is that the primary control on the phenotype comes from the efficiency of the mitochondria, and particularly a link between the protomotive force, the delta pH, and the mitochondrial membrane potential, which controls splicing and gene expression through the acetylation of proteins in the nucleus. And I may come back to the issue of ribonuclease reductase inhibition. Now, we've talked about the post-translational mutations of acetylation and methylation and phosphorylation, etc. All of these change how things function. And the acetylation of the histone is the protein on which DNA is held. That opens up the DNA so that the enzyme that transcribes DNA into mRNA can access the DNA and actually produce mRNA. In fact, the one hypothesis which has some evidence is that the acetylation process is part of what's called a metabolon, which goes through um, acetylating the histone and then transcribing it. So it's if you don't have it acetylated, it won't transcribe. But also,
May I ask a question?
yeah, of course you can.
So I once spoke with a scientist from China, and he was saying that there's like 100 different other ations, right, besides methylation and acetylation that affect the histones, and they're all over the map. The vast majority are not studied significantly, and they just partially because, like you say, they're hard to.
Well, it's hard to
Yeah,
measure because
yeah, hard to measure. Yeah.
if you take a cell and you then try and measure it by opening it up and getting access to it, everything changes.
Okay.
So to some extent, my sort of macroscopic do something, see what happens. Does hair grow? Does skin change? Do cataracts disappear? That sort of thing is an in vivo test where you have a hypothesis and you test the hypothesis. It's a bit like doing computer programming and debugging a computer program, because in the cell is the cell with all the PTMs and various other things is a bit like a computer. It sort of tries to assess, is there inflammation? So you've got NF kappa B, you've got NRF2, you've got HIF1 alpha, which indicate various levels of inflammation. How should the cell respond? Transcription factors. Look, let's just take vitamin D, for instance. Vitamin D, its primary function, as I see it, is actually as a transcription factor for about 1,000 genes, where those genes are exercised when vitamin D is available. And I think one of the reasons we have vitamin D in mammals is to tell the body when there's lots more food around, so you can transcribe and produce more proteins. Protein production requires a lot of energy, and if you're close to starvation, you don't want to be producing inessential proteins. But I think vitamin D is very helpful, but it's not essential, but it is very, very important. And I think that's one of the tests. So why do I focus on acetylation? Well, that's because I'm interested in working out what the development clock is. And I think the development clock is primarily driven by acetylation, and that
Okay.
methylation follows it, both on the histone and also on the DNA itself. But all of these things feed backwards and forwards. So everything, although I think it's upstream, and I think the point about this is that it is the status of the mitochondria primarily that defines the aging clock. Now, obviously, you've got lots of cells, and in each cell, you've got lots of mitochondria. And each mitochondria may have lots of different sets of mitochondrial DNA, which define the status of the mitochondria. So it's quite diverse in the body. There's not one clock in one particular place. So, sorry?
What do you mean different sets of mitochondrial DNA?
Yeah, so in any one mitochondrion, so in
Yeah.
a single mitochondrion, you may have, say, 10 different copies of mitochondrial DNA.
Oh, I didn't know that. Wow.
Yeah, it's very well. If you think about it, cells divide. When you've got stem cells, they divide. But the mitochondria lives its own life cycle. So mitochondria are fused together, they split up, they're recycled, and then they can create more, but they create them by splitting up mitochondria. And then separately, there is a life cycle of the mitochondrial DNA. And one of the interesting things, for instance, is DNA can be very badly damaged. There's a thing called the common deletion, where you delete 4,977 base pairs out of the mitochondrial DNA. And that often has a replicative advantage because it can be copied more frequently, more quickly than the longer normal mitochondrial DNA. And a second thing which I think drives aging is the presence of senescent cells. And the reason for that is the senescent cells produce SASP. We all know what SASP is. And that acts to reduce acetylation through actually the Janus kinase, which there's good evidence for that in terms of Janus kinase inhibitors because of their effects on the expression of the citrate carrier. So that's the hypothesis. And what we have to look at is what I call the citric acid bicycle. And many people know you've got what's called the TCA, tricarboxylic acid cycle, or citric acid cycle, or Krebs cycle. And that is where it goes round a cycle, malate oxalate. You can see it on the screen here. There's no sense me reading it all out. But there is also one called the non-canonical TCA cycle. And that starts in the same place with malate, which goes to oxaloacetate, which goes to citrate, but then that leaves the mitochondria through the citrate carrier, and that turns into oxaloacetate in the cytosol or in the nucleus. And that's an interesting point. And I'll come back to that in a bit. But that turns into oxaloacetate and acetyl-CoA. That then is converted back into malate and then goes back into the mitochondria. So these two cycles are going on, and some citrate goes all the way around the cycle, and some citrate comes out of the cycle, and it goes initially into the cytosol, although some mitochondria are actually attached to the nucleus, so it may go directly into the nucleus for some mitochondria, but most of them, those which are floating around in the cytosol somewhere, it will go into the cytosol. That's where the citrate goes. And then there's an enzyme called ACLY, and that enzyme converts citrate into acetyl-CoA. And acetyl-CoA is the primary substrate for acetylation. So your acetylation levels will be driven by acetyl-CoA levels, which is why this is that important. And so we look on then, yes, there, I got that there, which is, I've said that. So let's have the questions of how much citrate is coming out of the mitochondria. So partly, to get citrate out, you've got to start with pyruvate to go in at the top of the Krebs cycle, the citrate acid cycle. And that's driven by the proton motive force, or you could think of it as primarily by what's delta psi mitochondrion, which means delta is the change in psi, is the sort of electrical field. So delta psi m, the strange characters there, mean the mitochondrial membrane potential. It's actually the proton motive force, which is the mitochondrial membrane potential plus the variation in pH between the intramembrane space and the mitochondrial matrix. Also, you've got a gene, a protein, which is in the mitochondrial membrane, the inner membrane, which is sometimes called the citrate carrier and sometimes called SLC25A1. The SLC is solute. They're all the proteins that are in the membranes. And the SLC25 series are in the mitochondrial membrane, and they export or import or exchange different substrates. And obviously, if you've got more of this protein, more citrate can come out. And then a really interesting point is that it is actually the proportion of the ion, the citrate ion, which is 2 negative, that in part defines how much citrate comes out into the cytosol.
What do you mean pH is around 6%? 6%?
No. The pH is not at the normal matrix pH, which is like 7.8.
Is it percent though?
No, the 6% is the amount of citrate is in the 2-ion form. All right.
Sorry.
So citrate is an acid, and it can be 3-. So it's lost all of its hydrogen ions that it normally loses, its protons. Or it could be protonated. So it could be citrate, 3- plus 1 proton, plus 1 hydrogen ion. So it's citrate, 2-. And there's an equation called Henderson-Hasselbalch, which I'll come to in a bit soon. And at the normal matrix pH, about 7.8, you would get about 6% of citrate. But if we go on to the next, this is also linked to the mitochondrial efficiency, which is why the mitochondrial DNA matter. So if we look at this chart, this looks at the distribution of citrate species by the pH. Now, the physiological pH is 7.4, but that's not the pH that you get in the matrix of the mitochondria, which is a higher number. It's more basic. So pH is a measure of acidity. The lower number means the more hydrogen ions are around independently in the liquid. The higher number, so it's more acidic, and the higher number, the more basic it is, the more alkaline it is. And the way things are normally in the mitochondria is the matrix is more alkaline than the intermembrane space. And this chart was produced by an AI. I have checked it by comparing it to the values against in Wikipedia, which is, I wouldn't say Wikipedia is necessarily perfect, but they come up with a similar sort of thing. Now, the precise figures in here are going to be wrong because it's got the wrong temperature. And although the mitochondrial membrane, the mitochondrial matrix may have about 50% water, in practice, these things, it will be something different, but the principle is still the same, which is the vast majority of citrate at that sort of pH is either citrate 3- or protonated citrate, that is citrate 2- with one hydrogen ion. And the point is the enzyme, the citrate carrier uses protonated citrate. And the next step in the Krebs cycle, which is aconitase, uses 3- citrate. So if it's in a 2- form, it can go out of the cell. And if it's in a 3- form, then it can go round in the citrate in the Krebs cycle. And the significance of this is there could be, if you look at it, just taking the variation here for citrate species -2 as opposed to -3, it changes quite a bit between 8 and 7 pH. And the point is, there's this argument, which is, as the mitochondria varies, it's a very interesting question about, they're called the Zemel hypothesis about complex 1, as to whether complex 1 of the electron transport chain is actually also, to a certain extent, a potassium carrier. And as potassium transport is damaged, then the delta pH changes because the membrane potential goes down, but the delta pH goes up. And therefore, as that happens, that you get less citrate coming out of the mitochondrion. All right, now before I go on to that final page there, which looks more about how you can influence acetylation, that's getting quite into sort of mitochondrial function. Do you want to ask any questions at this point?
Too many.
So what is you said it goes to 6%. What is the normal percent?
Well, if you look at the chart here, all right, so at pH 7, you would have 20%
okay.
of citrate in the protonated form. Yeah, which is,
Right.
if you look at the top of the chart, H cit 2-.
Oh.
All right. So 20% at pH 7, which we know that's sort of like supposed to be neutral. And at pH 8, looking at that, I would guess that's about 4. It doesn't tell me the exact figure. I'm just guessing looking at the chart. That's quite a big
Right.
shift for a relatively small shift in pH. And the point about this is, if we talk a little bit about ACLY, citrate lyase, is an enzyme that converts citrate to acetyl-CoA and oxaloacetate. All right. Now, it's produced in the ribosome, of course, but then it can be acetylated itself, and then it can translocate to the nucleus. And if it's sufficiently acetylated, then what happens is it will process citrate in the nucleus. So you effectively have a flow of citrate which goes into the cytosol and the nucleus and is used separately. So in the cytosol, it's used primarily for cholesterol production and for lipid production. And in the nucleus, it's used primarily for acetylation of proteins. But the point about the acetylation of ACLY is as that acetylation goes up, there's more ACLY in the nucleus. And so there's more acetyl-CoA produced for the nucleus to maintain the acetylation level. So as I see it, that's a good argument for the level of acetylation to be an indicator of the biological age or development age. Yeah?
Yep.
Now, this goes on then to my chart about acetylation. I don't know how legible that is. Hopefully it's reasonably legible. So it's got small bits. So if we see here, you've got the mitochondria at the bottom, and the circle in the middle is representing the mitochondrial DNA, which doesn't really look like that, but it's not too bad. Citrate comes out of the mitochondria, it goes to citrate lyase, but the citrate lyase is not just in the cytosol, but also in the nucleus. And then the acetyl-CoA is used for various purposes, but there's a stream of a citrate that goes into the nucleus, potentially from a mitochondria attached to it, directly to it. And that's then available to do splicing and acetylation of the histone and acetylation of other proteins as well. And some of them, oddly enough, are inhibited by acetylation rather than actually improved in their activity. Now, let's going through the various things that then you can do. You'll start recognizing these things. Things you can do to improve acetylation. I always think number one is reducing mitochondrial damage. So avoiding high glucose. So now the figures in European SI are that if you've got a cell which is in, I think, 8 millimolar glucose levels or higher, then you're more likely to get more ROS. And if you get more ROS, you're going to get more damage to the mitochondrial DNA. Now, in American figures, that's roughly 144. So avoiding high glucose. The role of cerebral spinal fluid is interesting because I think what people miss is that melatonin acts as a protector of mitochondrial DNA, and that the cerebral spinal fluid is used by the pineal gland to distribute it to the central nervous system. And it is recognized that the central nervous system ages at a slower rate than the rest of the body. And I would argue, and there's good evidence for this, that that's because the central nervous system gets extra melatonin. And in fact, interestingly, children have much higher levels of melatonin. And there is evidence that melatonin holds back puberty. And puberty is obviously, although it's driven by hormone, the production of the cis-peptin hormone, it comes from splicing. So you have this aspect with children that have a tumor in the hypothalamus, which can block the production of melatonin. They get precocious puberty, and if you actually reverse that by getting rid of the tumor, then the precocious puberty fades and normal development ensues. And that's interesting because that's evidence for melatonin being the functional molecule that has that effect. Other antioxidants are more complex. So, and then going on the top of these things, recycle damaging mitochondrial DNA. Obviously, we all know about rapamycin, and I'm a rapamycin user myself. Inhibiting mTOR can create selective mitophagy, where the cell destroys the less efficient mitochondria. Now, there's an interesting point about this, which is that Chinese medicine, TCM there, has a number of yang qi type things like ginseng, ginkgo biloba, etc., so various herbs, and they are AMPK activators. And so what we see here is that in a traditional herbal medicine, there is a tool which is used to improve mitochondrial function. And the selective mitophagy is one of many systems of selective mitophagy, with a pink Parkin one. Fission mitophagy fusion is interesting because that deals with the fact that certain mitochondrial DNA mutations hide. So in other words, if you get a deletion in your mitochondrial DNA, and you've got like 5 or 6 copies of DNA, the protein can be produced by a different copy of the DNA. But at a point, which is called a level of heteroplasmy, you can't produce that protein, and then the mitochondria fails. And so what we have is fission to split up the mitochondria so that selective mitophagy can find the inefficient mitochondria, and then fusion to put them back together. And then additional substrate, well, I'm a fan of citrate supplementation, as people know. Additional citrate carriers, additional electron transport's an interesting one. I know I'm rushing through it all, but you could spend hours on each one of those, and we haven't got that much time. Inhibiting deacetylation is another interesting thing, because there's a lot of well-known histone deacetylase inhibitors, such as, for instance, berberine, such as curcumin, such as fisetin, such as quercetin. So there's a lot of the polyphenols tend to be HDAC inhibitors. A very interesting thing, well, is that when mitochondrial DNA is produced, it has nothing to fix when a building block from RNA, a ribonucleic triphosphate, is used rather than a deoxyribonucleic triphosphate. Whereas nuclear DNA has that. And there's a very complex balance between the different bases. And it means that roughly about 0.2, 0.25% of the time, the mitochondrial DNA has an RNA building block in it rather than a DNA building block. And then there is a question as to how you can work to reduce that error rate. And there are questions there as to whether eating additional DNA enables that to happen, although obviously that a lot of that's digested and doesn't end up in the cell. That's brewer's yeast, for instance. Or there are various pyrimidine supplements that can be used, which may or may not have a beneficial effect, because when it has the wrong building block, it works badly, but it doesn't work as well, and you get more mutations. Reducing the pH of the matrix is an interesting thing as well. I don't have a tool that works on that that I know of as yet. But all of those, I think, are tools which can be used to improve the level of acetylation and improve effectively the phenotype. So that gets to I've got lots more I could say, but I think that's probably enough today. I'm very happy now to just have a conversation.
Well, thank you. That was really interesting.
I'll say.
Should we leave this page up for the moment, because it's got a lot of data on it, or do you want to switch to people's faces?
I don't care what you look like.
All right. Well, it does. It's an interesting question, that actually, which is one that if you are managing to intervene on the main aging pathway, it will affect how people look. So, and this issue with hair color, for instance, that hair color can change midway down a strand of hair. It can go from being white hair to dark hair.
Yes.
And a lot of that, with particularly people like myself who have andropic alopecia, that's very obviously linked not just to the androgens, but also to mitochondrial efficiency.
What's Hunter Pellic and alopecia?
Male pattern baldness.
Oh.
Like I think we all have.
Yeah, well, I'm working on reversing it. It's happening very, very slowly, but it is reversing slowly.
I was about 1/3 gray when I graduated from high school, and as you can see, I'm 100% white now.
Well, we can't.
But I've no baldness whatsoever, so it's kind of weird.
I've got well, that's because that's partly genetic as well. So these things are affected by what your genes are, as well as where your development phase is.
Yes.
But
this is a great presentation. I could spend hours discussing each slide, it seems.
That's the whole point. But you see, the point about this is talking, this particular page looks at all the different interventions that people use and how they affect acetylation, but also how you can use them in a synergistic manner. Right? Because one of the big issues, you look at the What is it? The most robust mouse RMR, is that what Aubrey de Grey stuff with his mice,
Yeah.
where he's
Robust
trying.
mouse rejuvenation,
Yeah,
right?
robust mouse rejuvenation. Yes, that's right.
I was
RMR.
actually wishing he were here right now to argue with you.
Well, that's great. I'd love to have an argument with him, but he just disagrees that mitochondrial DNA matter, and that goes down to the Vermulst paper.
Wow.
And actually, if I go down here, this is some other things which I wouldn't do today because we haven't got this. This is my argument with Vermulst is this. It's actually transitions. There are different types of mutations, but I'm not going to do that presentation now because I think we've sort of having some questions on where we've got to is probably. I'm happy to do something else at some other stage, but I think the nub of this is that if you each one of these routes of intervention, you can't necessarily do them at the same time. Sometimes you can, sometimes you can't. There's an interesting thing. So, for example, a higher level of cytosolic acetyl CoA will inhibit some mitophagy. All right, so you don't want to supplement citrate when you're trying to do mitophagy specifically, if you see what I mean.
Mm.
So if you're doing a fast, you shouldn't be supplementing citrate.
Okay.
But all of these things, but by having a mechanism. Now, obviously, I could be wrong. I'm very happy to argue about it with people. In many ways, it's nice to have an argument. When you talk through things with people who disagree with you, you often learn a lot more than when you're talking with people who agree with you.
Yes.
So
Yes.
having debates is really good because it makes me do more work. But at the same time, well, any more questions?
Well, I'll just mention an observation
Yeah.
in the area that I have a little bit of specialization. It appears to be a general truism that slowing down development early in life is almost always a positive.
Yeah. Well,
And I'm not sure how that you mentioned that with the that disease where people
yeah, what is it? Hypothalamic hamartoma, I
yeah,
think it is.
yeah,
Um,
yeah.
the point is, well, my hypothesis is that the development clock and the aging clock are the same thing. So, and there's evidence that if you have precocious puberty, that if you're female, that you have an earlier menopause and you have
Mm-hmm.
potentially the disease of aging at an earlier stage. And it
Yes.
raises an interesting question because, and again, this is another presentation, which I shall just flash through the whole thing and go to, it's this thing here, if I can get it. Here we go, this thing, which is how a baby's born young, which I'm happy to do that presentation some other time as well. Because
I'd
obviously
love to see that one.
I have done, yeah, but there's a limit to how much we should do in one go.
Oh,
But
I agree. I agree.
the point is, when an egg is fertilized, that egg has mitochondria, and they are set at a particular development stage. But it's not the same for everybody. It's different, and that affects their it affects whether the egg actually implants in the uterus, but it also affects the life. Now, if you have worse mitochondrial DNA, you're likely to have earlier cancer, and you're likely to have other issues as well. And if you say, well, we're getting earlier cancer, earlier diseases of aging, earlier heart problems, is that because there's an issue with the mitochondrial DNA? Obviously, there are things you can do about mitochondrial DNA, which are listed here, because what you see, if we go back to this animal, all right, the one that went in reverse,
Mm. The walnut.
the sea walnut. So what happens to it to go in reverse? You starve it. It has severe selective autophagy, recycling mitochondria, getting more efficient mitochondria, and then it changes its phenotype to an earlier one.
Does the jellyfish do the same?
I haven't read up enough on the jellyfish, but I'm assuming it's the same process. I'm assuming
Hey,
it's.
Chris is here.
Who's Chris?
Chris Wickman. He's
Oh, hi, Chris. Sorry,
Hey,
yeah, I haven't got the list of participants up because I've got my screen in front of me.
yeah, sorry I'm
Um,
late.
no, it's all right. Well, look, we've transcribed it anyway, and it's on a video, so it's now at question time. What stage did you arrive at?
Just now.
Oh well, never mind. Well, what it is we were sort of looking at the final. If you don't mind, I don't want to go through the whole thing again.
No,
But
that's fine.
we were looking at the final thing, which is all the ways in which you can affect acetylation.
Yeah, I'll look at the recording again. Thanks, John.
Yeah, have a look at the recording. Well, the whole point about this was to do a recording, shove it on. I hope it's recording. Let me just have a look. I think it's recording.
yeah. I mean, every
Yeah, it
single
is
line
recording.
on this page could stimulate hours of study.
Every single line on this page could stimulate hours of discussion and study, yes. And
Yeah.
what's critical about it is that it gives you mechanisms for synergistic intervention. We're coming back to Aubrey de Grey's stuff, which is he's got his interventions, but he's really not quite clear what might be synergistic and what might be might be antagonistic, because you can have interventions that actually that individually are reasonably good, but when you use both of them, things are a worse result. So that's an interesting thing.
Could I ask you a bit of a derivative question?
Yeah, of course you can.
I've it's increasingly come to my attention that AKG is a powerful um, repair supplement.
Mm.
And you mentioned it a few minutes ago as part of a cycle, and I don't really know how it works, but I know it works really well.
Yeah, well, what it is AK. If I don't need
I
to get
think
my.
HMB has a similar effect, but either way,
I think AKG probably, if we go to the citric
there it
acid
is. Yeah,
cycle, um,
yeah.
yeah, in a sense, it's even more complicated because when you get AKG after isocitrate, so citrate gets changed into isocitrate, then to AKG. AKG at that point can either come out of the mitochondria into the cytosol, or I don't know exactly the balance between cytosolic and nuclear, but the AKG itself is a substrate for the TET enzymes, and the TET enzymes are the demethylation enzymes.
Oh,
So the presence of a higher level of AKG enables demethylation, amongst other things. So that's a relevant factor. Now, AKG will tend not to. The issue with citrate is I think primarily this thing about the mitochondrial membrane potential and the delta pH, and particularly the pH of the matrix. With AKG, it's a sort of blowback from there being enough ATP around. So because the mitochondria doesn't need to produce a lot of ATP. It produces some more AKG, and the AKG then says, "Oh, we've got enough energy at the moment, so let's perhaps use a bit more of it." Hence the demethylation.
really interesting.
But
Well, I
that
became
all of it,
aware of it, but there's a study by this guy Tatara,
yeah.
Tatara, with
I
pigs. It's amazing. It was like the sows were just fed a bit of AKG in their feed, and their piglets were better, dramatically better in every sense.
well, it's
Unfortunately,
yeah.
they killed them, and they didn't. We never know what the
What happens after
longevity
that? Yes.
aspect is.
I don't think it would. You see, some of these things are like they change a substrate without changing the fundamental structure. So the fundamental structure is your mitochondrial DNA and your presence of senescent cells. Um, if you add an extra bit of substrate, you can skew what it does, but the underlying structure is still the same.
Hmm.
So it may be that those piglets wouldn't necessarily live in longer, but they would be more healthy, as they could be. Because if you starve people, generally they're not necessarily that healthy, depending on the circumstances.
Right.
As we know, it's all complicated, and CR is a complicated issue. Um,
Well, everything, any addition to your health like say, for instance, if you have stronger bones,
Yeah,
well, that's
that's
not, there's no direct relationship between stronger bones and longevity. But on the other hand, it means you're less likely to have frailty, which means you're less likely to, so I mean,
exactly.
these,
So
these
it's
things
the
add
same.
up. Yeah.
It's the same with muscles, which is that
Yeah.
if you are limiting your food intake, it's going to have some effect on your muscles. And it may be when you get older, because we stand up, hopefully, and mice don't stand up, so they don't have such a problem falling over because they're already on the ground, whereas we do. And if we fall down, we may end up in hospital and then never come out.
Yeah.
And so it was interesting. There's been good stuff at the British Society of Research on Aging, looking at dealing with frailty. And
Right.
how you deal with people going into hospital. Well, a very interesting thing they found, which I got at the conference this year, was that if you're going into hospital and you do some exercise the day before going into hospital, it reduces some of the muscle loss you get from lying in bed. However, if you
Oh,
do it 2 days before, it's too late, too early rather, and in fact, you still get most of the muscle loss. I thought that was interesting.
that is interesting.
It's a useful
Well,
thing for
yeah,
people.
it's funny how frailty works. Is it doesn't kill you directly. It kills you indirectly by
Yeah,
laying you in a bed, and it's like a bed you never get out of, except
yeah.
to
Well,
go to your coffin.
yeah, it is difficult because obviously you then have those sort of patches of going to bed, getting more frail.
Yep.
And yes, you're not still not dealing necessarily with the mitochondrial DNA damage, but you are losing function.
Hmm. This is great. I can't wait to the next one. Thanks for this
Well, if you want
great
me to do another
presentation.
one, I'm happy to do another one. If this time works, we'll see. I'm happy to do these. I don't have a problem with it. I've got various ones that I do. We can discuss it on the GRG mailing list. Any more
Sounds good.
questions, or shall I end the call?
I did a screenshot of this slide because I want to study it between
Yeah,
now and
look
when
at
I
it.
see you
Yeah,
next.
well, if you want to study it, the web page has all these on it. Has a lot more things on it.
Oh,
The
okay.
citrate.science. I
Right.
can give you it in the chat if you want. Do you want me to put it in the
No,
chat?
no, actually I have because I took a screenshot. I have it
Well,
in my list of TBDs,
the,
you know.
yeah. Let me just get this up a sec. If I go on to chat, and if I put that there, all right.
Mm. Yep.
If you click on that, it just gives you it straight away.
Yep. Okay.
So on that point, are there no more questions?
Thank you,
Joey,
John.
Yeah, thank you, John.
thanks all for turning up, and I'm very happy to do this again. It's a useful thing to have these discussions.
Where will we find the link to the recording?
I will sort that out and put it on GRG.
Great. Thank you.
Bye bye.
Okay.
All right.
Cheerio.
Thanks
Take
very